Designers are required to calculate the deflection of beam during structural analysis. There are several reasons to avoid the beam from showing excessive deflection. First, deflecting beam may damage finishes or partition on top of it. Moreover, other structural members may not fit together if the beam deflection is out of control. Water ponding at undesired location may occur if there is no proper drainage system for the lowest point created by unforeseen deflection. The appearance of structure is less pleasing if the beams are showing noticeable deflection. We may use double integration method on Euler-Bernoulli equation to determine the deflection and angle of rotation of any point on the beam. This method follows Euler-Bernoulli theory, and therefore several assumptions need to be achieved. The beam should be made of an isotropic material, which ensures the mechanical properties are consistent for the entire beam. The beam should exhibit linear elastic behavior, where Hooke's law applies and ensures the modulus of elasticity E is constant. The cross-section of beam should be consistent, not only throughout the entire length, but also over the loading history. In this case, the second moment of area, I, for the cross-section remains the same. The deflection of beam is assumed small, which yields small deflection angle as a result. This simplifies the elastic curve equation and uses the current Euler-Bernoulli's equation. With these assumptions, it is possible to determine the deflection of beam using only one equation. As the name suggests, double integration literally asks us to integrate the Euler-Bernoulli equation twice. From the first integration, we obtain an expression contains elastic curve slope dv dx. Subsequent integration produces an expression contains deflection v. Note that during each integration, we need to introduce a constant, namely C1 and C2. However, the equation itself is not enough for us to solve any problem. The unknown constants need to be identified, and this can be accomplished by establishing boundary conditions. This is how a boundary condition may look like. The displacement and slope of deflection curve is 0 at the fixed end of cantilever. For simply supported beam, the vertical displacement at both supported ends should be 0. We may need to look up continuity condition if boundary condition alone is insufficient for us to solve body unknown. Let's say we have two different curve equations for portion 1 and 2 of a simply supported beam. At point C, the value obtained from first equation should equal to the value calculated using second equation. Let's look at a simply supported beam subjected to uniformly distributed load with increasing intensity. The length of beam is L, and the peak magnitude of the load is W. The beam reactions are first determined using equilibrium equations. Then, we need to determine the internal moment function. Based on the beam configuration and load pattern, we only need to cut the beam once. Therefore, we only produce one internal moment function, which is valid for any point on the beam, provided the origin is from support A. Let us substitute the bending moment function into the equation and perform double integration. It is time to apply boundary conditions. Focusing on the expression for vertical displacement V, and we know when x is 0, V is 0 since we assume there is no displacement at support. After substituting x equals to 0, we immediately know C2 is 0. Another boundary condition is when x equals to L, V is also 0. By substituting x equals to L, C1 is a constant dependent of W and L. After that, we substitute the expression for C1 and obtain the full function for slope and displacement. This function can be further simplified for the ease of future implementation. We may now implement the functions and determine the slope and deflection at key points. At both ends, The displacement is 0 but not for the slope of beam deflection curve. By substituting x equals to 0 and L, we can calculate those slopes. To determine the formula for the maximum displacement, we need to know where it will occur. It is important to know that at the point of maximum deflection, the slope of curve should be 0. Based on this condition, we can equalize the function of slope to 0 and try to solve for the x. By treating the resultant equation as a quadratic equation, we get to know the possible solution for x squared. By solving them, we found that x cannot be 1.315L since it is beyond the valid range of x. As a result, maximum displacement occurs at 0.519L from support A. By substituting this value of x into the displacement function, we obtain the formula for maximum displacement. Negative displacement value denotes the beam is deflecting downward, while negative slope means the beam is rotating in clockwise direction. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.